Thanks, Mike. Hello, everyone. My name is Chen Jiang from the Department of Engineering, University of Cambridge. It was my privilege to receive the award from the CSAR and to be here today to talk about my PhD research. Today, my talk is about low-cost, low-power organic electronics for wearables. In the view of the development of electronics, electronic devices has become smaller and smaller and more lightweight. And nowadays, if you look at the mobile phones, displays, and personal computers, they are getting smaller and smaller, and they can even put in our bags, in our pockets, and even they can be wear on our bodies. This makes us much easier to interact with electronic devices, to get in touch with friends and families, and also understand and manage our health condition. And it is wearable electronics that makes this concept and function more practical. However, the problem for wearable electronics is usually wearable electronics runs out battery very, very quickly. And wearable electronics requires different functionalities and different designs for electronics. You may know that if we want to change a design of electronics, it may cost millions of pounds, which means that it is important that we need low power and low cost electronics for wearables. In addition, the problem of conventional silicon electronics is it is rigid, and it is not comfortable to wear on a body. And you may see from this example. So in contrast, electronics based on organic materials, they can be flexible and they can be manufactured at low cost, which make organic electronics become a potential technology for wearable electronics. These requirements and features in wearable electronics motivate my PhD research on low-cost, low-power organic electronics. Today, I would like to show you two highlights in my research. The first one is all inkjet printed organic electronics. As you may have some ideas about conventional silicon device fabrication plant, it is very big and bigger than this room and maybe even bigger than the Churchill College. In contrast, what I have done here is that using inkjet printing, I formulate the inks for different types of materials, and I only rely on a desktop-size inkjet printer to fabricate and produce electronic devices. And you can see that the electronic devices can be fabricated by stacking layer by layer to avoid material wastage and also and it is material saving. So this technology is definitely low cost. And the second one is ultra low power organic electronics. Here is a typical current to voltage characteristics of a transistor. A transistor is a device that the current or the electrons flowing can be controlled by the voltage applied to it, like a tap, which the flow of water can be controlled by a valve. Okay, so normally the transistor is operated at the on state. in which electrons flows a lot and the current is high. So here I control the transistor to make it operate in the nearly off state. So the numbers of electron flow is reduced and the current is reduced. And by optimizing the fabrication process, the voltage to switch on voltage for the transistor is reduced to less than 1 volt, which, as you know, power is a product of voltage and current. This makes transistor power consumption is less than 1 nanowatt. Given a typical AA battery, if we operate the transistor in the on state, the battery lifetime is only 42 days. But if we do in this technology, the transistor the battery lifetime can be up to 15 years. This is ideal for wearable electronics because we don't need to change battery all the time, and even this low power consumption make batteryless operation becomes possible. So in the future, there are some challenges in this technology. The first one is because they are at very early stage, so there are some variations problem in this technology, and the frequency cannot go very high for computation. But it depends on how much we invest to this area. And in the future, I expect that electronic devices can be fabricated on threads or fibers that we can weave them into textiles and also made into smart clothes to wear on bodies. Finally, I would like to thank my sponsors for my PhD research and getting all these results and the CSARs. And thank you for your attending my talk. Thank you.
Great stuff, Chen. Time for a couple of questions, if you would like. Gentleman here, please.
How far are your wearables off being implants?
How far away?
How far off are your wearables being implants?
Could they be implanted in the body?
That's a good question.
Can you repeat the question, sir?
Yeah. Is it possible for a wearable device to implant into bodies, right? At this moment, no. But in the future, I believe it happens because the technology it will move to that because it is organic materials. It may be more comparable to our human bodies because our human are essentially made of organic materials, right? So they might be more comparability to bodies, yeah.
So there you are. You might have batteries grown on your liver or something. Sounds revolting. Sir?
If you were to sell these, how much of a supply is of these organic materials to use up?
How much
of a supply of organic materials is there?
You mean types of materials? Yeah. As you may know, organic materials is a very, very huge families of materials, and even actually the conventional electronics based on silicon, actually it is inorganic. There are plenty of material. So in organics, yes, we do have different types of materials that can be used as semiconductors, conductors, and also insulators. But now, because of this kind of research is still not commercialized. So a lot of materials are quite expensive. But if the researchers find out the very, very good material that can change or we say can beat silicon, then we can mass produce this kind of materials. And the cost of materials can be greatly reduced. Yeah.
So fields of electronic materials glowing in the sunshine. Last question here, please.
Thanks very much. A couple of questions, if I may. Firstly, what gate density can you realistically achieve? And secondly, how stable would the organic materials be over time?
Could you?
What gate density can you achieve, and how stable are the materials?
Okay. The density, gate density, this depends on the printing technology. So, if I would say now, the density is much, much, much less than silicon. But this depends on how are you going to use it. Because when we talk about silicon, the density should be high. We want to put as many as devices in the unit area. But for wearables, because our skin is large, so we don't have to. It's relative value, so about the density, right? So that's now I think the density compared to silicon is maybe a million less denser than silicon, but it depends how we can make better inkjet printers or printers, right? In terms of stability, this is also part of my research during my PhD. I managed to improve the stability of organic electronics. Normally, I heard from somebody else that their electronics, organic electronics, the lifetime is only 20 minutes after fabrication. How can it be used? So what I managed during my PhD is that I make it can live for 4 months already, and I still keep monitor how long is its lifetime. So let's see. Thank you.
Thank you.